Good morning, students. Welcome in next lecture of Math F242 Operation Research. Presently, we are studying the introduction of the basic probability. In previous classes, you have taken the idea of random experiment, sample space, events, random variables, and there, and you have seen we can characterize the random variable with the help of the two important probability function, PDF, probability density function, and cumulative distribution function. Thereafter, about the distribution, you can have the quick insight through some movements like mean, variance, and standard deviation. So you have seen how to drive the mean, variance, and standard deviation, where mean is the position parameter, and standard deviation and the variance are the variability parameter. It measure the variability or variation of distribution around the mean position or around the mean. Now, any doubt regarding the or in any topic, you can open your mic. If you have the doubt, you can open your mic instead of typing. So let us start the today's lecture. So in previous classes, we have covered single variable distribution or single random variable. Now we have the higher dimensional random variable. So let x1, x2, xn be n dimensional random variable. Means here we have the ordered pair of x1, x2, xn be n dimensional random variable associated with sample space omega. Some doubt? So sample space omega, sigma field f, and probability, associated probability, or you can say probability space, that is x1, x2, xn is the map from, because it is a random variable, so it is mapping from sample space to nth order real number. And from here we define the PDF and CDF. So P is equal to x1 is equal to x1, x2 is equal to x2, xn is equal to xn is equal to P of x1, x2, xn. So this is known as the joint distribution, or you can say this is known as the joint PDF. So if we have the discrete random variable, if x1, x2, xn are discrete, then summation for all xi of P is equal to 1, and integration over all xi of the PDF f is equal to 1 if x1, x2, xn are continuous. We can have even the mix of the discrete and continuous also. It is not necessary always all the n variables are discrete in nature, or always all n variables are continuous in nature. We may have the mixture of discrete and continuous, means some are discrete, some are continuous. So here the f and p both are joint PDF. Both are the joint PDF. From here we have the another type of marginal PDF, right, known as the marginal distribution. Marginal distribution state the density function for the particular variable. When we have the n variables, so out of the n variables we can consider the distribution of one variable, two variable, n minus one variable, right? So then we compute the marginal distribution. For example, if I want to find the PDF for the x1, probability density function for the variable x1, it means what I am interested for the probability x1 is equal to x1. So in that case, we take the summation of joint PDF. For the remaining variables, as x2, x3, xn. Similarly, we take the integration with respect to remaining variables x2, x3, xn, depending over whether the variables are discrete or continuous. By chance, if you have to compute only for the two variables, x1 is equal to x1 and x2 is equal to x2, at that time you have to take the integration over the x3, integration over the x4, and integration over the xn of the f with respect to dx3, dx4, and dxn. So this will give you the marginal distribution. Now, from the conditional probability, we have the idea if we have to compute probability A given B. So we have the formula probability A intersection B divided by the P of B, provided P of B not equal to 0, provided means event B has already occurred. So from here, if you want to write the probability that probability of x1 given x2, probability of x1 given x2, so probability of x1 x2 divided by the probability of x2. So in the numerator we have the joint PDF, and in the denominator we have the marginal PDF, marginal distribution and the joint distribution. So if you have to compute the conditional probability like this, so you have to use both type of the distribution. And by chance we are taking n variables, but it is not necessary all the n variables are dependent to each other. They may be the independent. So how we can recognize the independency? So we know that the formula for the independency from the basic probability theory. So here also we apply the same thing. Independency, when we have the joint distribution P of x1, x2, xn is equal to P marginal distribution for x1 into marginal distribution for x2 into marginal distribution of the xn. If x1, x2, xn satisfy this condition, then we say x1, x2, xn are independent. Similarly, by chance, if we have f of x1, x2, xp, y1, y2, yp, and that can be written as g of x1, x2, xp into multiply h of y1, y2, yp. So you can say that this set of the variable are independent to this set of the variable. So here the f is the joint PDF and g and h are the joint marginal PDF. Means when we have the more than one variable, then we say the joint, right, or higher dimensional random variable. And when we have the single, so simple, we say the PDF. From here, you know, in univariable we have the two important function PDF and CDF. So if we for higher dimensional random variable also we have the same type of the function. So now the CDF, so CDF we denote by the capital F. So f of the x1, x2, xn. So what we have the definition, it is the accumulation of the probability up to that point. So f of x1, x2, xn implies that probability of x1 random variable take the value up to the x1, x2 random variable take the value up to the x2, xn random variable take the value up to the xn. So this is equal to from the lower value to that point, accumulation of the probability up to that point, from lower value to that point, minus infinity to x2, minus infinity to x1, minus infinity to x2, minus infinity to xn of joint PDF with respect to x1, x2, xn will give you the CDF. So if you have to compute, means here again we have the if we have the joint PDF of the 5 random variable x1, x2, x3, x4, x5, and you have to compute the marginal PDF corresponding to x1, x3. So just you have to integrate for the x2, x4 and x5, right? You will have the joint PDF corresponding to x1 and x3. Now, from here we have very important conclusion. Uh, in practice, we have to add the random variables. So it means if you have to compute the a1 x1 plus a2 x2 plus an xn, and now you have to determine what will be the distribution of this resultant sum, where x1 x2 xn have the unique distribution. So if you define the y is equal to summation ai xi, where xi are the known distribution and y is the linear sum of the random variable. If y is linear sum of the random variable, it implies that y is also the random variable. Y is also random variable. So if xi's are independent, now the condition is if xi are independent, this condition is very important. Then expected value of y, why the expected value of y? Because y is the random variable. So expected value of y is nothing, it is the sum of, or it is the linear combination of expected value of the xi's. It is the expected value of xi's, that is the a1 e of x1 plus a2 e of x2 and plus an e of xn, right? So it is a linear combination of the expected value of xi, and this is possible only when all the xi are independent to each other. So for the two variable, we have the by definition we have this: let y is equal to a1 x1 plus a2 x2. If you have to compute the e of y, so by definition we know it is what? It is the value into probability. So integration corresponding to x1, integration corresponding to x2, right? So and so here we have the value is what? A1 x1 plus a2 x2 into joint PDF f of x1 x2 with respect to x1 and x2. Now this can be written as, if you take this constant a1 and a2 out of integral, so a1 integral minus infinity to infinity x1 f of x1 x2 into x2 dx1. So this will give you plus a2 minus infinity to infinity x2 into f of x1 x2 dx1 dx2. So if you take this integral, this function and this, if you are integrating with respect to x2, the joint PDF, it means you are computing what? You are computing the marginal density, that is the f of x1. So here it will become a1 integral x1 into f of x1, that is the marginal density. Similarly, here if you integrate with respect to x1, the joint PDF with respect to x1, it means you are getting the marginal density corresponding to x2, So now again what we have? Integral of value into probability, that is what? That is the expectation. So it will become a1 e of x1 plus a2 e of x2. So that is the e of y, So only the condition is if x1 x2 xn must be the independent. Similarly, if x1 x2 xn are independent, then variance of linear combination is equal to the sum of, or it is the summation of ai square and variance of individual, or variance of the univariable, uni-random variable. Variance of uni-random variable means if we have the variance of a1 x1 plus a2 x2, a2 x2. So this will give you a1 square variance of x1 plus a2 square variance of x2. In here we have seen students do the common mistake here when we have the minus. So it means here what we have to do, we have to compute the square of the plus minus a2, right? So always it will be the a1 square v of x1 plus minus of a2 square variance of x2, variance of x2, right? So here we have the plus minus of a2 square variance of x2. So here you have, if in this place we have the minus, need not to write the minus here. It is a very common mistake by the students. So please take care at this point. Now, so for that formula, we have seen that we are considering that x1, x2 are must be the independent. If the x1, x2 are not independent, then how we can compute? At that time, we know that variance of a1 x1 plus a2 x2. So by the formula, we know that for the variance, we know that e of random variable square minus square of e of x. So e of a1 x1 plus a2 x2 square minus e of square of e of a1 x1 plus a2 x2. If you open the bracket, so this will give you what? This will give you a1 square x1 square plus a2 square x2 square plus 2a1 a2 x1 x2. And we know that expectation follow the linear property. So this will become a1 square e of x1 square a2 square e of x2 square plus 2a2 e of x1 x2, e of x1 x2. Now when we open this bracket, right? So first e of, what is the meaning of the e of a1 x1 plus a2 x2? That is the e of a1 or a1 e of x1 plus a2 e of x2. Then we take the square. It will give you a1 square e of x1 whole square a2 square e of x2 whole square plus 2a1 a2 e of x1 into e of x2 Now if you take this term and this term from both, if you take the a1 square common, so a1 square common, in the bracket we have the e of x1 square minus e of square of ex1, right? From this term, if you take the a2 square common, so here we have the a2 square into e of x square minus square of e of x2, square of e of x2. So we know that what is this? This is the variance of x1. What is this? This is the variance of x2, right? Variance of x2. And in here we have the 2a1 a2 when we take common. In bracket we have the e of x1 x2 minus e of x1 into e of x2, So this is nothing. When the x1 x2 are independent, it is equal to 0. When x1 and x2 are independent, then this bracket will be the 0. Otherwise this is not 0, right? You have to write its value. When it is 0, then it will become a1 square into v of x1 plus a2 square into v of x2. It is true only when the x1 x2 are independent. Otherwise the above formula will work. From here we have another important term, covariance. Covariance measure the relation between more than one variable. So if you have to compute the covariance of x and y, it means it is nothing. We are interested for computing the expectation of x1 minus mu x into y minus mu y. So if the x and y, from here you can make one conclusion. If x and y are two independent random variable, then covariance will be the zero. But it is not necessary that if covariance is zero, then x and y are independent. Co X and y may haven't the unique relation. That's why the covariance is coming zero. But it is not independent. Independency implies covariance is equal to zero, but covariance is equal to zero will not implies the independency. Now, most important result from the joint, if x1, x2, xn are independent random variable. In most of the cases, we take the independent random variable and we have another random variable w, which is linear combination of random variables x1, x2, xn as summation of ai xi for I is equal to 1 to n, where ai are real numbers. Now, if you have to compute the moment generating function for the w, because why we are interested for the moment generating function? Because moment generating function is nothing, it is a fingerprint of any distribution. If you know the moment generating function, you can compute everything about the distribution. Because with the help of the moment generating function, you can generate any order movement, right? You can generate any order movement easily, and from those movement you can determine the different kind of the expectation, different kind of the measures. So as the moment generating function is the fingerprint, it is important to compute the moment generating function for the random variable, which is the linear combination of other random variables. So here, if you have to compute the moment, if the x1, x2, xn are independent, then moment generating function for the for the random variable w is nothing. It is the product of moment generating function of the random variable x1, x2, xn. That is the m of x1 a1t into m of x2 a2t and m of xn ant. So how we can compute? What is the basic formula of the moment generating function? It is nothing, it is the expectation of e to power tw, right? E to power tw, and w is what? Linear combination of the x1, x2, xn. So w is equal to a1 x1 plus a2 x2 plus an xn. So apply the algebra. This will become expectation of e to power t a1 x1 into e to power t of a2 x2 into e to power t an xn, and expectation follow the linear properties. So here it will become the e of into e of into e of, and that is nothing, that is the m of x1 of a1t, m of x2 of a2t, m of xn of an t. That is the product from 1 to n, m of xi ai t. So that is the most important formula from the joint. We will use this formula many times. Now, as I have told you, we will study many application oriented events, right, or probabilistic events. For that purpose, first we have to recognize, first we have to study, first we have to know some standard distribution. Then only you can apply these standard distribution in the application. So it is an important part. So before starting the standard distribution, first you must have the idea what is the Bernoulli trial. Trial means independent experiment, independent trial, independent experiment, right? Which independent experiment which has only the two possible outcome. For example, when we toss a coin, head and tail, success failure, up and down, left and right, right? So if in any random experiment we have only the two possible outcomes, that random experiment are known as that trial is known as the Bernoulli trial. And the probability of the success in that trial will be the P. So here we denote P as a probability of the success. So complementary probability 1 minus P denoted by the Q, it will be the probability of the failure. The complementary probability 1 minus P or Q we denote as a probability of failure. Now we have the very first distribution, Bernoulli distribution. So Bernoulli distribution is what? Here we say let X be the Bernoulli variate. Let X be the Bernoulli variate. Bernoulli variate. So first of all, it is the discrete random variable. It is the discrete random variable and its probability mass function or point probability function is given by fx is equal to p to power x 1 minus p to power 1 minus x for x is equal to 0 1, where p is the probability of the success or parameter for the Bernoulli distribution. For the Bernoulli distribution, so when we put f of 0, right, p x is equal to 0 means p to power 0 1 minus p to power 1 minus 0, that is the 1 minus p. So 1 minus p is what? It is the value of the it is the probability of the failure. It means here the 0 denote the failure, right? 0 denote the failure. When we put x is equal to 1, x is equal to 1, so p to power 1 1 minus p to power 1 minus 1, that is the p, that is the probability of the success. It means this represent the success. So the success and failure in the Bernoulli distribution can be characterized by the ppf or probability point probability function or probability mass function given by the p to power x 1 minus p to power 1 minus x. So first of all, you can see this f is greater than 0, greater than 0 or greater than equal to 0, right? For the both 0 and 1, for the both values 0 and 1, right? And you can see the sum of f, that is the f0 plus f1, f0 plus f1, that is the f0 is 1 minus p plus p, that is give you 1. It means summation of f is equal to 1. It satisfies the both necessary condition for being a point probability function or for being a probability mass function. So now you can say this is the ppf or pmf of the Bernoulli distribution. From here we can drive the expected value or mean, variance and standard deviation as ex is equal to p and vx is equal to pq and mxt is equal to e to expected value of e to power tx as q plus p into e to power t. So we know that what is the expected value by both method. Ex is what? Ex is what? It is the summation in case of the discrete random variable of the value into associated probability. So here the value is what? Here the value is 0, f of 0 plus 1, f of 1, f of 1. So it will become 0, f of 0 is what? 1 minus p plus 1 into p, that will give you expected value p. Similarly, variance of for x, variance of x is what? It is the e of x square minus square of ex. So first we have to compute the e of x square. So it is what? Discrete random variable. So summation of x square value into associated probability. So this will become 0 square f of 0 plus 1 square f of 1. That will give you 0 square 1 minus p plus 1 square p, or it is equal to p. So variance of x will become e of x square, that is the p, minus square of ex, and square of ex we have computed as a p. So this will become p. So if you take the p common, here we have the 1 minus p, that is the p into q. So that is the variance for the x. Then after we have the moment generating function for the Bernoulli distribution, e of that is the expectation of e to power tx. So if you have to compute the mxt in case of the discrete, or first of all it is the expectation of e to power tx. So in case of the discrete, it is the summation of value e to power t0 associated probability plus e to power t1 into associated probability. So that is the e to power t0 1 minus p plus e to power t1 into p. So e to power t0, that is the e to 0. So it will become 1 minus p plus p e to power t, and it is nothing, it is the q plus p e to power t. So that is the right, that is here we have the q plus p e to power t. And you also know we can compute the expectation from the mxt also. What is the ex? That is the dy dt of mxt at t is equal to 0. So dy dt of q plus p e to power t for t is equal to 0. So it is the p e to power t is equal to 0. So that will give you p. Similarly, if you compute the e of x square, that is the d2t upon dt2 of mxt at t is equal to 0. So it is the d2 upon dt2 of q plus p e to power t at t is equal to 0. So the first derivative will be the p e to power t, and then it will be the p e to power t for t is equal to 0. So when we put the t is equal to 0, it will give you p. Now after knowing the value of the e of x square and ex, you can compute the variance as a pq. It is also known as the point binomial distribution. After the binomial distribution, I will say again tell you why it is called as a point binomial distribution. Next is the binomial distribution. Right? Means this Bernoulli distribution is useful when we have to model in which we have only the two results, whether the product is good or not, whether the services is good or not. Right? When we have the two outcomes only, two possible outcomes only, then we use the, for the modeling purpose, we use the Bernoulli distribution. Now we have the binomial distribution. So binomial distribution, here x, here the x is the binomial variate. Binomial variate. This is also a discrete random variable, and it measure the number of successes in n Bernoulli trials, number of successes in n Bernoulli trials. Here the Bernoulli variate measures number of successes in n Bernoulli trials. For example, if you have the n machines, so how many machines are working, how many machines are non working? If you have to model this kind of the things, then we have to use the binomial distribution. Means out of the n Bernoulli trials, if you have to count number of successes, right, then you have to use the Bernoulli binomial distribution. And for the binomial distribution, since it is the discrete random variable, so we have the PPF or PMF, point probability function or probability mass function, as NCX, n choose x, right? N choose x or n combination x into p to power x 1 minus p to power n minus x. N minus x means n is the parameter which denote number of trials, and number of Bernoulli trials, and p denote probability of success in each trial. Probability of success in each trial. So its PDF, or you can say point probability function or probability mass function, is given by the n choose x p to power x 1 minus p to power n minus x, where x can take 0 success, 1 success, 2 success, or all we have the successes. And their mean variance are given as n into p, npq, and mxt is given by q plus p e to power t power n. So in this case, what I want to say, let us assume we have the 4 coins. We have 4 coins. So 4 coins may result head and tail, or you can say 6 coins. Okay, 6 coins, head and tail, head and tail, head and tail, head and tail, right? And we are defining the success as head. Now in the first toss we have the tail, in the second toss we have the tail, right? In the third toss we have the head, right? In the fourth toss we have the tail, in the fifth toss we have the head, and in the sixth toss we have the tail. It means here the x is equal to 2, number of successes in n trials. It is the number of successes in n trials. So probability x is equal to 2, right? Probability x is equal to 2. Now in now you please assume, right, each tosses, each tosses are independent to each other. And for each toss we have only the 2 result. It means this is what? This is the Bernoulli variate. This is what? It is the Bernoulli variate. This is what? It is the Bernoulli variate. This is what? Bernoulli variate. It means here the x is what? X is what? It is the sum of the n Bernoulli variate. It is the sum of n Bernoulli variate. Means it take the result 0 1, it take the result 0 1, it take the result 0 1, it takes the result 0 1, it takes the result 0 1, it takes the result 0 1. For the current example, it is the 0 plus 0 plus 0 plus 0 plus 1 plus 0 plus 1 plus 0. Here we have the 2. It means whatever the higher dimensional you have studied, that is now you can apply, right? So here if you take the e of x means e of x1 plus x2 plus xn, right? So expectation follow the linear property. So it is the E of x1 plus E of x2 plus E of xn, and you have derived E of x1 for the means here this x is what? Binomial variate. Binomial variate. Binomial variate, and these xi are Bernoulli variate. Bernoulli variate. Bernoulli variate. So it will become P P P, that is the NP. Similarly, if you have to compute the variance of x, that is the variance of x1 plus x2 plus xn, and we know that variance of variance of ai xi is equal to what? Summation of ai xi is equal to what? It is the ai square into sum of ai square into variance of the xi. So this will give you variance of x1 plus variance of x2 plus variance of xn. So this will give you a pq. For the Bernoulli variate, we know the variance is pq, 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 or it will become the npq. Means either you can compute by the definition, by that summation, or by this approach also, by using the property of the joint PDF. Then if you have to compute the mxt is what? Expectation value of the e to power tx, e to power expected value of e to power t, and x is what? x1 plus x2 plus xn, and it is what? It is the e to power tx1 plus tx2, tx2 plus txn, or this can be written as e to power tx1 into e to power tx2 into e to power t xn. So it is the e to power t x1 into expected value of e to power t x2 into expected value of e to power t xn, and it is what? It is the m of x1 of, right, it is the m of x1 of the x1 into m of x2 and m of xn, and it is q plus p e to power t, q plus p e to power t. For the Bernoulli, it is the q plus p e to power t and q plus p e to power t, that is the q plus p e to power t power n. But to apply this, it is mandatory to assume that x1, x2, xn are independent. Then only you can apply this formula, right? So automatically it is what? It is the product of the m of xi. That's the same formula you have studied earlier. Now when we put n is equal to 1, n is equal to 1, all the result will match with the Bernoulli. That's why we call the Bernoulli distribution as a point binomial distribution. Now, is there any doubt to understand the binomial through the Bernoulli? Anyone? Because here I want to introduce the theorems of higher dimensional. Earlier you have studied the same thing through the definition. Now geometric distribution. Here the geometric distribution is, means here the x is what? It is the geometric variate. It is geometric variate, and it represent the number of Bernoulli trials required. Number of Bernoulli trials required to get the first success. To get the first success. So it is the discrete in nature, it is the discrete random variable, and corresponding point probability function and probability mass function is given by q to power x1 minus 1 into p. Means failure, 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 then success. So first x minus 1 Bernoulli trials are failure, and xth and x Bernoulli trial will be the success. And here we have the x minus 1 Bernoulli trials are of failure result. Then we say, then it will give you the q, uh, q, 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 and p. That's why we have the q to power x minus 1 into p. Now, x vary from either you will get the success in the very first trial. So it is the 1, first failure, second success, 2, and so on. If you are unlucky, never you get the success. So and so on. Corresponding mean is equal to 1 by p. Variance of x is equal to q upon p square, and mxt is equal to p e to power t upon 1 minus q e to power t for the t less than ln of 1 upon q. Clear? So this is the mean. I am not going in the derivation part of this mean variance and moment generating function. You can revise from the probability part. I'm not going in the derivation part of this. Just you have to remember the mean for the geometric distribution is 1 by p. Variance is q upon p square, and mxt is equal to p into e to power t upon 1 minus q e to power t, where t is less than ln of 1 upon q. Then after we have the another distribution, Pascal distribution. So Pascal distribution is nothing. It is the extension of the geometric distribution. In the geometric distribution, we have count the number of Bernoulli trials required to get the first success. Here in Pascal, the Pascal variate X measure number of trial required for the Rth success until the R successes. Until the R successes, how many trials we require? So for that, again we have the means for the R successes, minimum R trials required. Minimum R trials required, or you may require R plus 1 trial or more trials and the ppf corresponding ppf is right f of x with parameter r, number of successes, and p is the probability of the success in each trial. So f of x r comma p, it is equal to x minus 1, choose r minus 1, p of r q to power x minus r, right? And Pascal is nothing. Pascal distribution is, it is nothing. It is the sum of n independent geometric variate. It is the sum of n independent geometric variate, right? It is the sum of n geometric variate. Means geometric variate measure first success, number of trials required to the first success, number of trials required to get the first success, number of trials required to first success. So it is the R. So number of trials required to get the first success, number of trials required to get the first success, number of trials required to get the first success. So it will measure the number of trials required to get the R successes. So as we have done for the binomial, here also if you take the expectation expectation of x, that is the expectation of x1 plus expectation of x2 plus expectation of the xr. And from the geometric distribution we know it is the 1 minus 1 upon p, 1 upon p, r upon 1 upon p. It is the r time, so it will become the r upon p, r upon p. Similarly the variance, so variance will be the variance will be variance of x, that is the variance of x1, variance of x2, and variance of xr. So it will become q upon p square, q upon p square, q upon p square, that is the rq upon p square, rq upon p square. Similarly, if you have to compute the mxt, so mxt is the product of the mxi, where xi is the geometric distribution. So this will become, right, product of p e to power t 1 minus q e to power t, and r times we have to multiply. So here we have the power r. So that's why here we have the all the things. So you can understand with the help of the n or r independent geometric distribution. So in next class we continue this thing. If you have any doubt, please ask.
Sir,
Yes.
sir, what is the range of the x values for Pascal distribution?
Pascal distribution range, it minimum value is r, because for the r
Yes, sir.
successive is required, so at least r Bernoulli trials required,
So R plus 1, R plus 2, and so on. That's it.
and so on.
Okay,
If you are unlucky,
okay,
never
okay.
you will get the r successes, na? So it continue
Yes, sir.
to the
Yes.
infinity. It continue to the infinity.
Okay, sir. Okay. Yeah. Thank you, sir.
Any other doubt?